All right. So good morning, everybody. Welcome to our ninth class. Now,
Good morning, sir.
good morning. So let's see. Okay, good, excellent. Let's see. So already the number of people coming to class has dropped. This is what happens every time. This looks like a 9. It should be a 9. So last time we had I clarified all these questions about entanglement, expectation values, etc. Right? Then I had asked you in the last class to watch. Oh, I forgot to share the YouTube URL. By the way, even if I don't share the YouTube URL, you can find it on my. If you go on my channel, you'll see that it's whatever is live streaming, it will show up. So it's not going to be an issue. Okay, so once again. All right, so I had asked you to watch, I think, videos number 14, 15, and 16 of the PS703 class. Now, those videos were about operators on this tensor product spaces. So that's one thing. Then second thing is completeness relationship. That's another thing. And what else was there? Let's see. That was lecture 14. Then
Commutators.
Lecture 15. Sorry. Why don't you tell me? I think it'll be faster that way. So
Commutators.
Sorry. Commutators and what else?
And squares, Cauchy squares inequality relation.
Cauchy-Schwarz inequality. So basically leading up to the uncertainty principle. Okay, great.
Yes.
So did you watch the derivation of the uncertainty principle?
Yes, sir.
Okay, good. All right. So operators on tensor product spaces. Then the next one was what was the next one? This completeness relationship. Completeness relation. Then one second. I'll be right there. 1 second, guys. I'll be right back. Thank you so much. सही बात है उसकी। ठीक है, ज़्यादा भी क्या करना लो। हाँ नहीं नहीं ठीक, थैंक यू. Okay, yeah, sorry, I guess I forgot to unmute myself. I was just getting a cup of tea actually because I was feeling very, very, very sleepy right before class. So, yeah, so commutators and then commutators leading up to the derivation of the uncertainty principle. So the uncertainty principle, that is something that you have encountered before. It has generally been introduced to you without only with respect to you have seen it only with respect to, let's say, position and momentum operators, right? But it's much more general than that. It applies to any two operators which don't commute. Much more general. Okay, so sorry. Now, so let me begin. Questions? This is supposed to be a question answer session, right? Anybody?
Sir, in the end of 16th lecture, like
Ah,
you did something like you told us that let psi A be eigenstate of A and psi B be an eigenstate of B. And then you told us that let A and B not commutate, like they not have any common
ah,
eigenstates. And then in the end, like what was the derivation that you did after that? Like in the end, you proved it equal to zero.
right. Okay. So that's the question of simultaneous diagonalization. Okay. So basically, if you have two operators which commute, then the statement is that they can have the same eigenstates. Okay. So now the thing is that, see, you remember that the measurement process is that you have some state. It can be on this state you can conduct a measurement, and you do so by you measure some operator, right? Now, and it's a Hermitian operator. And since it's a Hermitian operator, that means it has a complete set of its eigenstates form a basis for the state space. That means your state can be expanded as a superposition of eigenstates of this operator, right? So these are eigenstates of this operator, right? So when you make a choice of the operator, right, that determines your basis. When that determines your basis, right, then after measurement, what happens? You have collapse. What does the state collapse into? It collapses into one of these possibilities. With probability lambda k square, right? Remember this?
Yes, sir.
Now the thing is that let's say that we conduct another measurement. Okay. So first we measure with B with this operator A, and then we conduct another measurement. Okay. With operator B, and B of course has to be a Hermitian operator, etc. Okay. Then again we can write down the state psi as a sum of superposition of eigenstates of B. So this is with a prime. So these prime states and these prime eigenvalues, they are eigenvalues and eigenstates of B. Right? So what will happen? The state will again, this whatever was the state previously, that will collapse into one of the phi k prime squared, phi k prime with probability lambda k prime squared. Okay. Now here's the thing. If A, B is not equal to 0, if this commutator is not 0, then they cannot have the same set of eigenstates. Okay, so basically, if a state is an eigenstate of A, then it cannot be an eigenstate of B, and vice versa, if the operators don't commute. Okay. Right? I mean, if you have a vector, it can be an eigenstate of more than one operator, right? There is no, for example, an example of this is that you remember we have these operators, sigma, x, y, and z, right? Now, these operators, so well, this would be a, but yeah, this is also fine. But I'll give a different example. When we talk about the a particle with angular momentum j, right? What are the eigenvalues? If you we will talk about this next week also. By the way, next week I want you all to please attend the regular BTech classes from 8 a.m. because I will be talking about the simple harmonic oscillator Schrodinger equation. And so that is something that I want all of you to be present for. Okay. So the statement is that if you have this angular momentum operator, then this angular momentum operator, right? There are two eigenvalues. One is J, one is M, right? What is J? J is the total angular momentum. M is the what do you call it? The magnetic quantum number, right? So if J goes from, if J is equal to 3/2, then M can take values from -3/2, -1/2, 0, 1/2, comma 3/2, and so on, right? All of these things I think are covered in the BSc syllabus. But again, next week when we discuss harmonic oscillator and all, we will derive all of it. Okay, so there's no need to worry about it. So we have these operators. Now all of these operators, they don't commute with each other. They have the same properties as the sigma x, y, and z. Out of these operators, we can construct another operator, which is the total angular momentum squared. Okay. This total angular momentum squared, the eigenvalues are something like this. Okay. Now, I think the square root sign, it would be there. Right. Now the thing is that if you look at this set of 4 operators, okay, and all of these are operators, they will all have their own eigenvalues and eigenstates, right? Now, what is J? What is the small j? The small j is the eigenvalue of J square, the full J square operator, the full angular momentum. What is M? This is the eigenvalue of Jz, right? So the question is, why? So I can write it like this, let's say J comma Mz. Okay. We don't normally put this subscript Z. I'm just putting it there just to emphasize the fact that This is the angular momentum and the eigenvalue of Jz. So why not? Why do we label states like this? Why not J comma mx my mz, right? Where mx y are the angular momenta along the x and y axis, right? Why can we not do that? The reason is because these operators jx, jy, jz, and jz, jx, all of these operators are not equal to 0. The commutators are not equal to 0, right? This is all covered in homework 2 and 3, right? Now, since these operators are not 0, we cannot simultaneously diagonalize them. They cannot have simultaneous eigenstates, right? So for example, see this state ket Jm. This is a simultaneous eigenstate of J square and of Jz. See, its eigenvalue with Jz is m, and its eigenvalue with J square is J times J plus 1. Right? So this is a single vector, and there are two different operators, J square and Jz. They both have the same eigenvector. Right? But this guy will not be an eigenvector, not be an eigenstate of Jx and Jy. Okay. So again, so what Shantanu is asking is the thing I have shown in that proof at the end of lecture 16, and that is a statement that if you have two operators which and so the reason they have the same eigenvector is because they commute, because their commutator is 0, right? Now the commutator of Jx, J square with Jy and Jx is also 0, right? So then you might ask, why can't I choose Jy and Jz instead? So the thing is, you can choose Jx or Jy. But if you choose Jx, let's say you choose J square and Jx, okay? But then you can't have Jy and Jz. Why? Because these two guys do not commute with Jx. So these two are the commuting operators, right? So this is called having a complete set of commuting operators, also given the CSCO like this.
Excuse me, sir.
Right.
Excuse me, sir.
Mm-hmm.
Sir, what is it that is unique about JZ? Like why we are using JZ?
There's nothing unique. It's more or less just convention, right? I mean, it was just the experiments were done in such a way that the spin was measured in the axis perpendicular to what we consider our level surface. Right? We have this concept of Z going up and XY in the plane determined by Earth's gravitational field, right? So it's just a accident of history, really, that the people who first did the experiments, they measured Jz. They could have measured Jx and Jy also. right? So in that case, you would be talking about something else.
Yes,
But it
sir.
doesn't matter what you choose, right?
Yes, sir.
Your physics will remain the same, right?
Yes, sir.
Okay. So the point of that derivation is that if you have two operators which commute, then they have a set of common eigenstates. So if they commute, then there exists a set of vectors such that these vectors are eigenstates of the A operator and they are eigenstates of the B operator. But they can have different eigenvalues, but they are still eigenstates. That whether or not A and B commute, right? So if you take A and B, the product of AB, and you act on this phi k, what do you get? You get A times B acting on phi k, which is A times what is B acting on phi k? Lambda k prime, because phi k is an eigenstate of B. Now this can be written as lambda k prime times A times phi k, because lambda k is just a number, lambda k prime. And this becomes lambda k prime lambda k phi, right? Because phi k is an eigenstate of A also, right? Now if you reverse this, if you say B times phi k, you will get, by following the same procedure, you will get the same answer, right? The order of these two numbers doesn't matter because they are just numbers, not operators. And so this is equal to A times B times phi k, right? Shantanu, are you following
Yes,
me?
sir. Yes, sir. Yes, sir.
यार yes sir बोल दिया करो ना थोड़ा फिर. So if you look at these two expressions and you bring both of the terms over on one side, right, you get that the commutator of AB acting on phi k is 0, right?
Yes, sir.
ठीक है ना? तो अब what is the physical relevance of this? The physical relevance of this is the fact that this is why I was talking about measurement. It's like, let's say you take a system and you perform a measurement of the system with operator A. And then after that, you perform a measurement of the system with operator B. Okay. So, sorry, 1 second. So we have our system. We perform a measurement of this system with operator A. Then we perform an measurement of the system with operator B. Okay. The other choice we have is to go in the different direction. Okay. Now, the thing is that if A and B commute, right, then you'll end up in the same place. You'll end up with the same final state if A and B commute. Okay. But if they don't commute, then this will lead you to one state. Let's say psi1. This will lead you to a different state, psi2. And these are not the same. So the end result is that if A and B are 0, then you can perform a simultaneous measurement of both operators. Okay.
Yes, sir.
So that is what I think is shown in lecture 16 on the last and the end of that lecture.
Yes,
Does
sir.
this clarify that, or
Yes, sir. Yes, sir.
I've tried to give the physical motivation also. I think the physical motivation is elaborated on in lecture 17 onwards. Okay.
Yes, sir.
Next question. So what is the bottom line? The bottom line is that if AB is equal to 0, then they have a common set of eigenstates, and one can perform simultaneous measurements of both of these observables, right? Now this leads us directly into the uncertainty principle. If they don't commute, then if you take a measurement of A and then you measure B, or you measure a B, then you measure A, you get different answers. Right?
Yes, sir.
So if you have X and P, they don't commute. So that means that there will be, if I measure X, then the measurement of P will be uncertain. And if I measure P, then the measurement of X will be uncertain. There is a simple way to see this. Consider these two Pauli matrices, sigma X and Y. Okay. Or let's say sigma X and sigma Z. Now they don't commute, right? And what are the eigenstates of sigma Z? Eigenstates are, let's say, 1, 0, and 0, 1, right? And then what about sigma X? What are the eigenstates of sigma X? They are 1, 1, and 1 minus 1, right? Divided by root 2, normalizing, right? So what happens if I start with some state psi, which is in a superposition of the up and down states, alpha, beta, and then I measure sigma Z, okay? What will happen if I measure sigma Z? Let's say I get the answer is +1, and the output, the final state is then 1, 0. Okay. But now the thing is that this 1, 0, it is a superposition of these two states. This is a plus state and a minus state. This 1, 0 is a superposition of the plus state and the minus state. I think this is also in the homework set. So now I know sigma z. My uncertainty in sigma z is 0. But what is the uncertainty of sigma x in this state? The uncertainty of sigma x is maximum. That it can either be the plus state or the minus state. Okay. Again, I don't know how much this clarifies. I hope it clarifies something. Okay. Next question. Questions? Anybody? By the way, if you're watching on YouTube, okay, Yash is watching on YouTube. Okay, thank you for putting your names on the YouTube channel. That way I know that who is watching this. So this is about this commutators and diagonalization. All right, then there was this completeness relationship. The completeness relationship is very important. So it says that if you take a set of eigenstates, a complete set of basis vectors, and you ask what is this operator, so then this is equal to the identity. So first of all, there are a number of things about this which are very important. One is the fact that if you take a state psi and you take another state phi, then you can write down this guy, something like this, phi times psi. As Nishita had pointed out in the previous class, this is not the tensor product, this is the outer product. And this outer product turns big, this is an operator now. Okay. So I can write this operator as a matrix. And what are the matrix elements of this operator? The matrix elements are phi I and psi j star. So this is your, if you have if this corresponds to an operator O, then the matrix elements of this operator are phi I psi j star. Okay. And this statement is saying that if I take this operator O and I take the trace of this operator, right? Well, no, it's not saying that. So if you take these, each one of these is an operator, right? So if you sum over these n operators, what you get is the identity matrix. And this identity matrix, this can be used in many different ways. So as one example, so I'm sorry, I'm just talking on and on here, but I'm waiting for any questions from you all. Again, my assumption is that you have all watched 14, 15, and 16, and that you have worked out you know, the calculations in those lectures. So are there any questions, clarifications, anything?
Hello, sir.
Yeah.
Hello.
Yeah. Tell me.
It's
tell me.
about the Hilbert space.
Tell me.
In an example you have taken a coin tossing.
1 second, okay? Don't mind, please. I'm
You are
just getting a 1 second, please. I'm getting a
you
call.
have to
Pranav, 1 second, please. I'm very sorry about that interruption. Yeah, Pranav, you were saying something about Hilbert space. Please go ahead.
sir, you are told that when
Hello?
tossing a coin, the dimension of the Hilbert space is given by 2 raised to n. Hello?
The product.
Dimension is given by 2 raised to n.
What I think.
Hello, sir. Can you hear
2
me?
raised to the nth power, right? That is when you take the, yeah, you're little, yeah. Hello? Hello,
Yes,
Pranav?
sir.
So you are saying that basically if you take the
are
tensor product of Pranav, can you type your question in the chat because your voice is not clear? Can you type your question in the chat?
Okay. Yes.
Please. I think your connection is a little bit it's not good. My connection is good, but it sometimes it can be a little unstable, but otherwise it's good, thankfully. So unfortunately, internet services for different people in different areas are not the same. So you can always type your question in the chat and I can answer that there. In the meantime, anybody else has a question? So I'm just waiting to see what Pranav's question is. Any questions, anybody? Hello? Hello, Sudeep, I think there's some disturbance from your end. Pranav, are you able to type your question? Okay, I don't know. Maybe he's typing. Okay. If Shubham is asking something on YouTube, if the outer product output is 0, again, I don't understand exactly what you're asking me, Shubham. But the outer product is basically, okay, Pranav's question has come. Dimension of Hilbert space is given by M cross N of 2 matrices. M cross N of 2 matrices. I'm not sure what you mean by that. See, if you have a vector space, if we say that the vector space has a dimensionality, if we say that the vector space is n-dimensional, what do we mean by this? It means that any vector for all vectors in this vector space, any vector can be written as a superposition of some set of vectors EI, right, which are where these vectors are orthonormal, right? This is what it means to say that the vector space has some dimensionality. This means that if I write down the components of V, then it has n components, right? And operators on V, right? An operator on V, an operator is something which takes V, right, to V. In other words, if I take a state psi for a state psi in V, then if you have an operator, it acts on this state, it gives me another state, that state is also in V. And what are these operators? These operators are, they are n by n matrices. Okay. Yeah.
It's been told that the dimension of Hilbert space A combos in tensor product dimension of Hilbert space B is given by dimension of Hilbert space
Okay.
A
Okay. That's what you mean,
dimension of
right?
Hilbert space B.
Right. So if you have dimension of two of a tensor product space, so I have two vector spaces V and W, okay? And I take the tensor product space. What is the, so that is dimension of V multiplied by the dimension of W, okay?
So in that case, when we call the toss coins.
No. So I'm
three coins.
For 3 coins, okay. So then 3 coins, each coin has a each coin has a Hilbert
dimension
space
of 3.
No.
Half.
Each coin has a Hilbert. You're not listening to what I'm trying to tell you. You have 3 coins. Each coin individually has how many states? Pranav?
3 states. 3 states.
I'm asking about 1 coin. I'm not asking about 3 coins. I'm asking about 1 coin.
1 coin has 1 state.
Hey, Bhagwan. 1 coin has how many possible output? Heads and tails. How many states is that?
2. Head or
2
tail.
states. So what is the dimension of the Hilbert space of 1 coin? Okay.
2.
Now, if you have three such coins, then what are you doing? You're taking the tensor product of 3 such Hilbert spaces.
Oh.
So what is the dimension?
Okay.
8. See, now, okay, what you are saying now, it's I can understand where that confusion is coming from. Because when you're talking about 3 coins, right, the natural sort of thing to think is, well, okay, maybe if I have 3 coins, I can describe them like this. Okay. But that is not what 3 coins is, right? What is this? What is this? This is a single vector, right? And this vector is 3-dimensional. So this is not 3 coins. This is actually a 3-sided coin. Do you see the difference between these two things? So imagine that you have a dice. Okay, you have a dice, your normal ordinary dice, which has 6 faces. Okay. All right. So this is a dice with 6 faces. Then I write down the Hilbert space for this dice. I say that this is a quantum dice. Okay. What will be the dimensionality of the Hilbert space of this dice? Anybody? Pranav?
6.
Right. The dimension of this Hilbert space will be 6. So there are 6 possibilities, right? You can get 1, 2, 3, 4, 5, 6. Those are your 6 possible outputs. Pranav, are you following?
Yes.
Now imagine that you have a system where you have 3 such dice. Okay. What will be the dimension of this Hilbert space?
To the power 3.
6 raised to 3.
6 raised to the third power.
216.
Right? So what you were talking about was not 3 coins. What you were talking about was a 3-sided coin. So if I have a dice, how would I describe the state of a dice? I would describe it using 6 numbers. Right? And then the state of the second dice, how would I describe it? I would also describe it using 6 numbers. And the state of the third dice,
Beta 1, beta 2, beta 6.
again, I would have 3 numbers. What is the total number of numbers? Right? So the general state of the system, I would describe how? I would describe the general state as alpha I, beta j, and gamma k. For 3 dice. Right? So for instance, if you roll the 3 dice and the first dice comes out showing 1, and the second dice comes out showing 3, and the third dice comes out showing 5. How would you write the state of the system? In terms of the ket vector, what would be the notation I would use? What would go in here? Anybody? What is alpha I in this case? One. And alpha and beta j? And gamma k? 5. right? So you would write down the state as in this way, ket135, right? Assuming that you are numbering your dice from 1 to 6, right? In the case of our for a spin 1/2 system, we are numbering we have a dice, but the two states of the dice, we are numbering them as 0 and 1. Instead of 1 and 2, we say 0 and 1. In this case, we are numbering the states a little differently. So it's 1, 3, 5. Otherwise, if you use the same numbering, then this would be 0, 1, 2, 3, 4, 5. And in which case this would become 0, 2, 4. Right? So again, now let me ask you, if I write down a state of this form, okay, 1, 2, 6 plus 1, 3, 5. And divide by 2. This is a state of 3 dice system. Okay, it is a superposition of these two possibilities. Okay, probability that the first dice will give 1. So can you look at this state and tell me what is the probability that the first dice will give you 1?
One.
That's 1, right? Because when you measure this system, what will happen? You will get outcome will be either the state 1, 2, 6 or the state 1, 1, 3, 5, right? So in both of these cases, the first dice, this is the first dice, right? The first dice is showing me the number 1, right? The same way I can ask what is the probability that the second dice will show me the number 4? Answer will be 0, right? Because this state doesn't have any component where the second dice is 4. Okay. So I hope that the question about dimensionality of Hilbert spaces and all is clear. Let me just clarify it again by giving you a slightly different example. Imagine that you have a system which consists of something like this. A single spin 1/2 particle and a 6-sided die. Then what is the total dimensionality?
12.
Dimensionality is 12. Right? How would I write down the states of that system? I can write them in many different ways, but I'll choose one way. I'll write them in such a way that the first two states would be the states of the coin, and then these ones will correspond to the states of the dice. I can choose some numbering like this. But in quantum mechanics, very strange things can happen. What can happen? I can start off with a state which looks like this, but then I can make a transformation of the state. I can perform a rotation, unitary rotation of psi. When I perform a unitary rotation, what will happen? These components can get mixed up together, right? I can end up with a state which has a mixture of both coin parts and dice parts, and it's hard to tell which one is which one. Right? So this is another example of how quantum mechanics is different from classical mechanics. Okay, so I hope that the dimensionality question is clear. Okay, next question. So we have talked about dimensionality. We have talked about commutators. I have explained why commutators are related to uncertainty. And it has to do with the fact that you cannot diagonalize two non-commuting operators at the same time. And also this, then we mentioned this completeness relationship and outer products. Okay. And right. And again, want to emphasize that outer products and tensor products are not the same thing. An outer product gives you an operator, a tensor product gives you a vector. So if I take a tensor product of two vectors, I get a third vector, which is in a bigger Hilbert space. But if I take an outer product of two vectors, I get an operator, which acts, well, the dimensionality of the operator depends on the dimensionality of the two vectors, but it's an operator, not a vector. Okay, questions? Okay, so for next week's classes, tomorrow is a Eid, I believe. So next week's classes, Tuesday to Friday, we will meet at 8 a.m. Okay, and the reason is because I will be talking about this thing, the harmonic oscillator Schrodinger equation. Okay, and so this is very important. This is basically introducing you to things like these dagger operators, A and A dagger and all that. And okay, and you have to keep in mind that the MSc syllabus will naturally be more involved than the BTech syllabus, right? So in the BTech syllabus, I am reaching this harmonic oscillator at the end of the semester. For them, only 2 more weeks are left. But for you, we have to cover a lot more material. We have to talk about, we have to talk about in more detail. We have to talk about things like tunneling and finite potential well, and a Coulomb potential. What happens in a Coulomb potential, and then some more properties of entangled systems, which goes beyond what is covered in the BTech syllabus. So technically it's supposed to be the same class, but obviously the BTech students are not as well prepared as you all are. So questions? Any other questions?
Can you share the exact syllabus of this course? Okay.
Sure. I will send you something by Monday. Okay.
Okay, sir.
All right. So let me see on YouTube. Okay, good.